Hey guys, welcome to lecture number 4 of this video series. So we were in module number 5, which deals with the chapter consolidation. So today we will be starting off with something called spring analogy. This was developed by Dr. Carl von Terzaghi. Now Terzaghi is considered as the father of soil mechanics or the father of geotechnical engineering because of his immense contribution in this field. In fact, he was the first to demonstrate the process of consolidation in soil. Today we'll be looking at one of his experiment over here. So as you can see, there is a vessel over here where he took some amount of water and a spring. Okay, he also attached a dial gauge over here which is missing in this diagram. Anyway, then he took a pipe which contained a valve over it. So valve is something which is used to control the flow of water, right? So now we are in stage 1 where the valve is completely closed. So since the valve is completely closed, no water is allowed to drain out of the vessel. Now what he did, he applied a load P into the setup. He found that the dial gauge gave some reading and the spring did not show any kind of change. It neither compressed nor it got elongated. So what did he conclude from stage 1? He said that when the load is applied, initially all the load is taken up by the water and no load is taken up by the spring. Okay, since the dial gauge gave some reading, he was sure that the load is taken up by the water itself. So mathematically, if we are to represent this situation, we can write that total load P is equal to PW, that is load taken up by the water, and PS, which is load taken up by the spring. Now we know that the spring neither elongated nor compressed, so it did not took any kind of load, and hence we write PS is equal to 0. So ultimately we have got the entire load taken up by the water itself, that is P is equal to PW. Now let us move to stage 2. In stage 2, what he did, he partially opened the valve. Okay, so some amount of water was allowed to drain out of the vessel. Now since the amount of water has now decreased in the vessel, it is not able to take up all the load imposed on it. So now the spring will take some amount of load, and as a result of which it gets a bit compressed. So mathematically, if we see, the load taken up by the water has now decreased by an amount delta P, and this decrease in load is now actually taken up by the spring. So you can see PS has now become equal to delta PW. So this is the mathematical condition for stage 2. Now let us move to stage 3, where the valve is completely open and all the water has now been allowed to drain out of the vessel. So now no water is there in the vessel, and as a result of which the entire load imposed is taken up by the spring itself. So you can see here that PW, that is the load taken up by water, has now become 0, and as a result of which P is equal to PS. So the entire load is beared by the spring and it gets compressed to its maximum value. So this is the experiment carried out by Terzaghi. Now he compared this experiment to soil. He said that the spring resembles to the soil particles and the water actually resembles to the pore water present in the voids of the soil. He said that when a load is applied on a soil mass, initially at the very instant the load will be taken up by water, but gradually the water will start to drain out of the voids, as a result of which the load will now be taken up by the soil solids, because of which it it will be getting compressed, or you can say it will decrease in the overall volume. And when the water has been fully drained out of the soil mass, the entire load will be taken up by the soil and it will be fully consolidated, or we can say that the volume has been fully decreased. So this is the process of consolidation from Terzaghi's point of view, and since this is compared to spring and water, so it is known as spring analogy. Alright, now let us see the Terzaghi's theory of one-dimensional consolidation. So from the same experiment he gave further deductions. Now you see why I have written here one-dimensional consolidation. Actually consolidation is a three-dimensional phenomena, right? but analysis of a three-dimensional process in this stage is not possible. So hence we consider consolidation to be one-dimensional. So when I say consolidation is one-dimensional, it means that water is draining out in the vertical direction only. It can either move downwards or it can move upwards. So you can see that water is moving in the direction of y-axis only. So it becomes a one-dimensional consolidation. Anyway, so in this theory he gave some assumptions which I request all of you to study from a standard textbook. Okay, so let me get straight into the theory. According to his theory, he said that the change in pore water pressure, okay, so here u is small u, the small u denotes pore water pressure and t denotes time. So the rate of change of pore water pressure is directly proportional to the square of change of pore water pressure with respect to distance. So z here denotes distance. So mathematically del u by del t is directly proportional to del square u by del z square. Now we know that whenever there is proportionality, there comes a proportionality constant. So in the next step you can see del u by del t is equal to Cv into del square u by del z square. So Cv here is the proportionality constant. So Cv is known as coefficient of consolidation. Now Cv or coefficient of consolidation is also expressed in a different way, that is Cv is K by mv into gamma w, where K is coefficient of permeability, mv is coefficient of volume change, and gamma w is unit weight of water. Now if you put the unit of coefficient of permeability and coefficient of volume change and the unit weight of water, you will find that the overall unit of Cv turns out to be meter square by second. Okay. Now let us look into a different term called degree of consolidation, which is denoted by capital U. So what is degree of consolidation? It is the percentage of consolidation taking place in a soil mass. So if I ask you what is the percentage of consolidation in a soil mass, and if your answer is 60%, then it will mean that 60% of water has been drained out of the soil. Okay. Now degree of consolidation can be calculated in three ways. Let us look at each of them. The first is in terms of settlement. So in terms of settlement, degree of consolidation is given by del HT by del HF into 100. Now what is del HT? Del HT is settlement at any time t, and del HF is the final settlement. So what are these? Let us try to understand. Suppose there is a soil which is fully saturated, that means all the voids are occupied by water, and I saw that all total it has got 100 liters of water. Okay. Now let us assume that after 5 years 20 liters of water has been drained out. So since water has drained out, there will be decrease in the volume, and as a result of which there will be some amount of settlement. So let us assume that the settlement after 5 years is 10 centimeters. Okay. And after 20 years all the water has been drained out. There is no water left in the voids, and because of the water draining out fully out of the soil, there will be a final settlement which I say that it is 20 centimeter. So in this case del HT will be 10 centimeter, that is at any time t it is 10, and del HF, that is the final settlement, will be equal to 20. So degree of consolidation will be 10 by 20 into 100, that means it is 50% at time t equal to 5 years. Okay. So this was in terms of settlement. Now in terms of void ratio, degree of consolidation is E0 or E0 minus E, or you can write this as ET also. Okay. E0 minus ET, divided by E0 minus E100 into 100. So what is E0? E0 is the void ratio at time t equal to 0. So you have already known that at t equal to 0, when a load is applied over a soil, the load will be taken up by the water only. So the soil solids will not undergo any change in volume because they are not taking any kind of load, right? So the void ratio in that case will be the maximum. So E0 is the maximum void ratio. E100 on the other hand is the void ratio when there is 100% of consolidation. That means all the water has now drained out of the voids. So now the soil solids will be very close to one another, and hence the void ratio will be the minimum, and hence E100 is the least value out of all the E's. Okay, and ET is the void ratio at any time t. That means it is in between E0 and E100. So this is how we calculate degree of consolidation with respect to void ratio. Third, it is in terms of pore water pressure. So just like the previous case, we use the same formula, that is U0 minus U or UT divided by U0 minus U100, where U is the pore water pressure at time t equal to 0, U is pore water pressure at any time equal to t, and U100 is pore water pressure at 100% consolidation. Now you see, when there is 100% consolidation, there will be no amount of water left in the soil mass. Okay, so since there is no water, so obviously there will be no pore water pressure. So we can write U100 is equal to 0. So this is what you can see in the next step. U0 minus 0 becomes U0 only. So this is the formula to calculate degree of consolidation in terms of pore water pressure. Now let us look at another term which is known as time factor of consolidation. Before that, the time taken for a soil, which is denoted by small t, is inversely proportional to coefficient of consolidation, and it is directly proportional to the square of drainage path. Okay, drainage path is denoted by small d. Now what is a drainage path? Let us try to understand. So here you can see I have taken a soil mass, a fully saturated soil mass to be precise, whose height is h. Okay. Now on one side it is completely sealed, there is no empty space on this side, but at the bottom I have given some porous stones. So since it's a porous stone layer, water can pass through this layer. Now you see, if I apply a load over here, water will start to drain out, right? So in which direction it will drain out? It can only drain out through the porous layer of stones. So the direction of water flowing out will be vertically downwards. So what is the drainage path in this case, or what is the distance through which the water can travel? It is equal to h, right? So drainage path is equal to h when it is a single drainage setup. Now when it comes to a double drainage setup, I have got porous stone at the top as well as at the bottom. Now when I apply a load over here, water has got two paths. Okay, it can either flow upwards or it can flow downwards. So some of the water will rise to the top and it will drain out, whereas some of the water will go down and then it will drain out. So in this case you can see drainage path, or the distance by which the water travel, is getting half of h. That is, it is equally divided into two parts, right? Now coming back to our original situation, we got that T was inversely proportional to CV and directly proportional to the square of drainage path. So here I can write, combining both of them, as T is directly proportional to d square by CV. So since there is proportionality, again comes a proportionality constant which we call as TV, capital TV. So if I again rearrange the terms, I get TV is equal to CVT by d square. So this TV is actually known as time factor of consolidation. Okay, TV is time factor of consolidation. Now time factor can be also expressed in terms of degree of consolidation, that is capital U. So when degree of consolidation is less than 60% or equal to 60%, it can be expressed as pi by 4 into U by 100 square. So let us assume that U is 40%, then time factor in that case will be equal to pi by 4 into 40 by 100 square. Okay. And if your degree of consolidation is greater than 60%, then you are to use this formula. Okay. So that's all for today. See you in the next class.